Okay, so I think we're just about ready to get started. So welcome to the monthly seminar of the Working Group on Active B stars. This month's seminar is being given to us by Dr. Pablo Reig, so it's my pleasure to introduce him. Dr. Reig is a researcher at the Greek Foundation for Science and Technology, as well as the University of Crete, as I just saw on your slide. But Dr. Reig also got his Bachelor in Physics from the University of Valencia and the PhD in Astrophysics from the same university. Dr. Reig, without further ado, I'll let you take it away.
Okay, I'll share the screen. Okay, I hope you see it. Okay, thank you, Alex. Thank you, everybody, for being here. I'm going to talk about the BeXB binaries. I'll be presenting mainly my work, but I try to select more recent results, but always with the idea to talk about the general properties of BeXB binaries and not focusing on any individual system. So the word binary implies two components, and in this case we have the B star and the neutron star. These are two completely different types of astrophysical objects. One is at the beginning and the other one at the end of their lives. One is bright, luminous, and generates its own energy, talking about in the optical band. And the other one is also bright, but in the X-ray band, and not because not by itself, but because of the processes that are going on in its vicinity. Here I'll talk about these two components separately, but at the end of the talk we'll see how these two components interact, and as you know, the way they interact is by producing an X-ray outburst. But before that, I will give
Sorry,
a short...
Dr. Reig.
Yes?
I believe you've forgotten to put it in the presenter mode. We're just seeing your first slide and
Okay, so it doesn't work.
Now we're seeing your outline, yes.
So I should leave that like that, okay? Because otherwise... you're telling me that the presenting mode is not working?
No, we're not seeing it. Maybe you need to try to share the presenter view, but we were just on the first slide and not seeing anything. Sorry for the interruption.
In that case, okay, let me, sorry. Let me try a different thing here. Problem is that I guess I have to activate the share screen after the presenter mode, but in that case it is not possible because I don't see the Zoom part. Okay, so I'll use a different share screen.
Yeah, possibly if you do share screen and then.
And I remove this and probably remove drawings and more standard.
Okay, this should be pretty good, yeah.
Okay.
Sorry
about this. Okay, so now you see the second slide.
Yes.
Okay. Sorry. Okay, so I was saying that I'll talk about one of these components, but at the end we will see how they interact. But before that, I will give a short introduction. Now, there is no point in describing what a B star is to this audience. You are all expert on the subject. But I will spend a few minutes to describe the different subclasses of BeXB binaries that we know, and how our knowledge has changed on high-mass binaries over the course of years. So, from a historical perspective. Okay, So as I said, I mean, you all know the definition, the tradition. This is the traditional definition of a B star. Okay, but let me remind you what are the three main observational properties of B stars. And these are, they show emission lines, they have infrared excess, and the light coming from the B star is polarized. Okay. Now, all these three properties can be attributed to the presence of a circumstellar disk around the equator of the B star, and two considerations should be given here. First, this is not an accretion disk. This is a disk that is not formed by an external source of matter. On the contrary, it's formed by matter that it is ejected from the B star. And that's why these days everybody, most people refer to the disk as a decreation disk. They use the word decreation. And also the other important characteristic is that it's not a permanent feature. The disk forms, grows, expands, and dissipates on time scales of typically of years. Now, in terms of the X-ray properties, basically, virtually all BeXB binaries are X-ray pulsars with spin periods in the range from a few seconds to a few hundred thousand seconds. They also present cyclotron lines in the energy spectra, and this is important because the cyclotron lines provide the most direct way to estimate the magnetic field. And it turns out that the magnetic fields in the X-ray binaries are of the order of 10 to the 12th, 10 to the 13th Gauss. On the long term X-ray characteristics of the X-ray binaries are characterized by two types of outbursts, the so-called type 1 and type 2. In the type 1 outburst, the X-ray luminosity typically doesn't go above 10 to the 37 x per second. These are relatively short outbursts in the sense that they last for a fraction of the orbit. But the most characteristic property of these outbursts is that they are orbitally modulated. In contrast, type 2 outbursts are giant events where the X-ray luminosity may reach Eddington values. And they generally last for a few orbits. Okay, and well, this is the picture that everybody has in mind when we talk about BeXB binaries, with the neutron star orbiting around the B star and the interaction with the disk. So let's now see how our knowledge on high mass X-ray binary has changed over the course of years, starting with at the start of the X-ray era, back in the 60s. The first galactic X-ray source to be discovered was Scorpio X1 back in 1962, and a few years later, the first X-ray pulsar was detected. The first report of X-ray pulsation, is a paper by Giacconi in, I think, 1971. So our tour will start in the early 70s. So I'm going to use, I just cut and paste a text from the relevant papers to illustrate this evolution. So back in the early 70s, the main issue was to try to understand what those galactic X-ray sources were. And although it was not 100% sure, but the preferred model was that the galactic X-ray sources were binary systems. Okay, as you can read there in this paper by Barbich back in 1972, many, if not most, of the powerful galactic X-ray sources are generated in binary star systems. They had to explain also the X-ray emission, and that was more or less clear in the sense that the accretion was the process giving rise to those X-rays, right? Mass escaping from the secondary star will follow the highly evolved primary. Now, notice that here primary is called the neutron star, and the secondary is the B star. And for us, people doing high mass X-ray binary is the opposite. But people doing low mass X-ray binary, they usually call the primary star to the compact orbit. Well, if they were X-ray binaries with a compact companion, yes, you can. The primary can either be a white dwarf, a neutron star, or a black hole. A few years later, the binary model consolidates, and people understood that there were two different types of binaries with high and low companions. One group of sources is associated with a late O or early B supergiant, but there were other sources with a much later spectral path. Also, B star were identified as best candidates for transient X-ray sources. Sudden variations in the rate of mass ejection from B stars in the presence of a compact companion could produce transient X-ray emission. Then, okay, for now I'm going to focus on high mass X-ray binary only. And in the early 80s, it was clear that there were two different types of high mass X-ray binaries depending on the luminosity class of the primary companion. So we had supergiant X-ray binaries that were persistent sources, and the X-ray binaries were transient sources. The BeXB binary are found to be systematically wider systems with lower mass primaries and with significantly transient behavior than the standard massive X-ray binaries. Now, because of their brightness and because of their persistent emission, supergiant X-ray binaries were thought to be the dominating population of high mass X-ray binary, while BeXB binary were considered as atypical cases. As more and more systems were discovered, supergiant X-ray binaries were further divided into two different classes: high luminosity and low luminosity supergiant X-ray binary. And the difference between the two, and with respect to the transient BeXB binaries, was the way in which mass was transferred. In one of the most cited papers, I think, in the field, Robin Corbett, back in 1996, wrote, "A natural way of accounting for the separation of high-mass pulsators into three groups is by invoking different mass transfer processes." So in BeXB binaries, the matter is available for accretion came from the circumstellar disk around the B star, while in supergiant X-ray binaries we had wind-fed systems. Accretion comes from the stellar wind, and also the third possibility is accretion through Roche low overflow. In this case, an accretion disk is formed. This happens in systems with very narrow orbits, very compact binaries. Now, in the 90s, we realized that persistent BeXB binaries also exist. Until now, the BeXB binaries were considered as transient sources. And these persistent BeXB binaries were low luminosity X-ray emission. They showed lower luminosity than the transient BeXB binaries, and were associated with slowly rotating pulsars, with spin periods typically of a few hundred seconds compared to the few seconds, a few tens of seconds of the transient BeXB binaries. Now, at the beginning of the century, in the 2000s, that I would call it the golden decade, because in terms of the number of new systems that they were discovered, especially thanks to XTE. So until then, as I said, BeXB binaries were mainly transient and eccentric systems with eccentricities above 0.3. And that was because of the kick that they received during the supernova explosion. So it was a surprise to see that there are also BeXB binaries with nearly circular orbits, which means that they receive a much smaller kick at the time of formation. Another subclass that show up was the gamma gas-like objects, with the prototype is gamma gas. And these were BeXB binaries where the optical properties were very similar or identical to the well-known BeXB binary class, but the X-ray properties were completely different. The X-ray luminosity was very low, 10 to the 32, 10 to the 33 x per second, and it was more, it has a more thermal origin rather than the non-thermal inverse Compton of the BeXB, typical BeXB binaries. Now, there are a number of models that have been put forward to explain these gamma gas-like objects. From some group of people thinks that there is a white dwarf instead of a neutron star. Another group thinks that there is a rapidly spinning neutron star, and that you get such a low X-ray luminosity because it is in the propeller effect. So matter is spun away when it tries to reach the neutron star. And other models like collisions of winds of a hot helium star with the B disk, or even magnetic interactions between the B star and the disk. Another interesting result was that it turns out that among the supergiant X-ray binaries, transient sources also exist, and these were called supergiant fast X-ray binaries. Supergiant fast X-ray transients. This was a completely unanticipated result, and the credit goes to Integral mainly. This was the discovery of this system, and they are transient sources with a very sharp rise, reaching the peak of the flare in less than an hour, in tens of minutes, and the duration of the outburst is also much shorter compared to BeXB binaries, in the range of 3 to 8 hours. Okay, now the next decade we witnessed the first detection of a B star with a black hole. This system, MWC656, through radial velocity measurements, Casares reported that the minimum mass of the compact object is 4 solar masses, so I concluded that it must be a black hole. However, these results have been questioned recently with more data, with more observations, and apparently this black hole companion is ruled out by new observations. Instead, the most likely companions are maybe a white dwarf, a neutron star, or even a hot subdwarf. Finally, in the next decade, we also became aware that there are binary systems in which we have a B star, but that most of the high energy radiation is emitted in the gamma ray range from above 1 MeV. And these were given the name BE gamma ray binaries. Okay, so this is the zoom of BeXB binaries, and I stop here for the introduction, and let's now start to dissect the binary. And I will first talk about the B companion. Now, talking about the B star means talking about the B, but also talking about the E, that is, talking about the massive, bright, early type star, but also about the disk. Obviously, separating the emission from these two components is not easy, but we can turn to the different variability timescales to get some, at least some, to distinguish between them, because the typical variability timescales of the B star is of the order of hours to days, while the typical variability timescales of the disk is much longer. It's weeks, months, or years. And we also expect to get different information from the two. From the B star, we expect to get information about how the disk is formed, while by monitoring disk emission, we expect to get information on how the disk evolves. So the variability related with the underlying B star is, of course, rotation. B stars are fast rotating stars. On average, they rotate at about 80% of the critical velocity, although some extreme cases has been reported with rotational velocity up to 99% of the critical velocity. What you see in this figure is the rotational velocity for different spectral types, and the lines are this represent the critical velocity and 80% of the critical velocity for two different evolutionary phases. So the fact that we see the data points populating or being close to the lines means that indeed B stars are fast rotating stars. But rotation alone is not enough to explain the majority of the observed phenomenology. And the other fast time characteristic of the underlying B star is pulsation. B stars are non-radial pulsators. So the non-radial pulsators divide the stellar surface in regions with different velocity fields and with different temperatures. If the amplitude of the pulsation, if it is large enough, we can see these pulsations as in the spectroscopy and in the light curves as a line profile variation or as a changes in brightness. Okay. And in fact, one possible scenario that has been put forward for the formation of the disk is that matter is ejected when non-radial pulsations are in phase, because some works have shown that in this case the amplitude may increase as much as an order of magnitude. And here you have some examples of line profile variations and brightness variations. Probably you know, but this the John Teltis website has a number of animations, very illustrative, to see how these moving patterns of peaks and troughs move from the blue to the red in time scales of hours to days. On the right-hand side, you have some representative examples of light curves with high cadence. This corresponds to the data from the TESS mission, the Transiting Exoplanet Survey Satellite, and some characteristics periodograms corresponding to those light curves. Okay, but all what I have said so far has to do with classical B stars, but I am interested in BeXB binaries. So the question is, do B stars in BeXB binaries pulsate? So in order to answer this question, what I did, together with Professor Fabregard from the University of Valencia, we analyzed all the data that we could find from the test in the test archive. And what you see there is on the left hand side is the normalized light curve, and on the right hand side is the characteristic, the periodogram. For some systems, just you can detect pulsations or oscillations by eye, even just by looking at the light curves. But if you compare all these, these different periodograms for all these different sources with what we see in classical B star, you see that we observe the same phenomenology. So basically, the phenomena you find in B stars that are part of BeXB binaries is very similar to B stars. We see group of sources in the periodograms, or we also say observe isolated high frequencies. red noise in some cases at low frequencies, and all this has been very well studied for classical B star. Here you have a particular example of this well-known BeXB binary, where you have the light curves, the normalized light curves, and the periodogram. The interesting thing in this slide is the fact that you notice that during the brightening phase, the amplitude of the pulsations is much larger than during the decay phase. And it is, you can see that for the black part, the blue part, and the green part of the light curves. Okay, you compare the rise with the decay, how larger the amplitudes are, the amplitude of the oscillations. And this has been interpreted as mass ejection episodes. And that's why this has been suggested as a possible scenario for the formation of the disk in the B star. Okay, what about then the disk variability? Well, as I said before, the typical variability time scales are from weeks, months to years. And if one wants to monitor the disk, the best observable is the H-alpha line. The H-alpha line is the prime indicator of the state of the disk. Not only because in the intensity, the strength of the line, the strength of the line gives us information of how big the disk is, how big the disk has developed, but also the shape, the profile of the line, because it tells us about how matter distributes in the disk. Okay. Now, the difference, basic difference between a classical field B star with a B star in a BeXB binary is the presence of the neutron star in the binary. So, a fair question to ask is, how does the neutron star affect the disk? The answer is truncation. And what is the observational evidence that we have for truncations in BeXB binary? Was one piece of evidence comes from this diagram, or this plot, this figure. Here I'm plotting the equivalent width of the H-alpha line as a function of the orbital period. So what this plot is telling us is that systems with long orbital periods, wide orbits, tend to show larger values of the equivalent width or equivalently larger disks, while systems with short orbital periods show smaller disks. The explanation for that, well, the most straightforward explanation is that in binaries with short orbital periods, with narrow orbits, the neutron star prevents the disk from expanding. Another interesting results concerning the disk is how fast the disk grows. And what you are seeing here is a number of BeXB binaries. In this case, is the equivalent width of the H-alpha line as a function of time. That is the evolution of the H-alpha equivalent width. And these systems are ordered in increasing value of the orbital period from the top left to the bottom right. But what I've done here is, for those systems that went through a disk loss episode, and we know that because we see the equivalent width going from negative to positive. Of course, the sign is purely conventional. It's a convention. Negative values means emission lines. Positive values of the equivalent width means absorption lines. But okay, when you see absorption lines, it's because the disk is dissipated. So what I did is just a simple linear fit from minimum to maximum after one of these low optical states, and plotted the slope of these lines, straight lines, as a function of the orbital period. And we got this nice correlation. Now, here I don't say, I mean, this plot must not mean that systems with long orbital periods, the process that ejects matter from the photosphere, the B star is different, has different mechanisms that in short binary. That would be very difficult to explain. What I think, or my interpretation here, is that because of truncation, matter accumulates in a smaller volume in narrower systems, narrow orbit systems. Okay, and it is this increase in the density what gives this faster growth in the equivalent width. Okay, this will mean the end of part one of the talking about the B star, and we can summarize that due to this truncation, BeXB binaries have smaller disks and probably denser disks. The B star in BeXB binaries has the same physical properties as classical field B star in the sense of the pulsational properties. So the neutron star strongly affects the evolution of disk through the truncate, but it does not seem to affect the mechanism that ejects matter from the photosphere. Okay, let's now talk about the other component, the neutron star, and necessarily we have to go to the X-ray band. The neutron star in BeXB binaries is a strongly magnetized neutron star. So the magnetic field disrupts the accretion flow at some distance from the surface of the neutron star and forces the accretion matter to follow the magnetic field lines onto the polar caps, creating what is known as hotspot and a structure known as a accretion column. Now, the conditions prevailing in this accretion column define two different accretion states or accretion regimes. These are called supercritical and subcritical accretion regimes, and they are called like this because at certain value of the luminosity, the structure of the accretion column changes. Basically, the difference is how the accretion flow is decelerated. At high luminosities, in the supercritical regime, a radiation-dominated shock stops the flow at certain distance from the neutron star surface, as you can see in the figure. So at high luminosity, the radiation pressure dominates, and the breaking of the accreting matter is due to interaction with photons. Okay, it's the fact that the plasma is decelerated by radiation pressure. In the case at low luminosities, in the subcritical regime, there is no accretion, radiation shock, and the accretion flow goes all the way into the surface of the neutron star, and it is decelerated through collision. Now, the transition between the two states occurs when the luminosity reaches a certain value, and this luminosity, for obvious reasons, is called the critical luminosity. Now, from the theoretical point of view, the critical luminosity is a rather difficult quantity to compute because it depends on parameters that are not well constrained. It's not only that it depends on the mass and radius of the neutron star, but it also strongly depends on the geometry or the size of the accretion column and the magnetic field of the neutron star. It depends also on the opacity, which means that it will also depend on the energy, polarization state, and temperature of the photons. But basically, it is strongly dependent on the geometry of the accretion column and the magnetic field. So it would be good, it would be nice to have a way to estimate the critical luminosity from the observations. And I'll come back to that later. Okay, so again, this question has already appeared in this talk, is what is the observational evidence? Observational evidence for the existence of these two accretion regimes. Okay, I said that the critical luminosity strongly depends on the geometry of the accretion column, so we expect to get information from the pulse profiles. Now, again, from a theoretical point of view, when we are in the supercritical regime, when the radiation shock is present, this radiation shock is optically thick, so photons cannot escape along the magnetic field lines, and they escape through the walls of the accretion column, and this is known as a fan beam. In the subcritical regime, there is no shock, and the photons can indeed escape along the lines, and this is known as the pencil beam. Now, in terms of observations, I mean, this translates into observations in that as the X-ray luminosity increases, the pulse profile changes from a single peak to a double peak. Okay, and this has been interpreted as a change in the structure of the accretion column and the formation of the radiation shock. Okay, in reality, what you have is a contribution of both kind of beams, fan beams and pencil beams. Okay, but you see that this changes as the X-ray luminosity increases. So this is one piece of evidence for these two accretion regimes, but I also said that the critical luminosity strongly depends on the magnetic field. So by studying the parameters, the variability in the parameters of the cyclotron line, we may also get some information about these states. And indeed, when you plot the energy of the cyclotron line versus intensity, X-ray intensity or current rate or flux, you observe two different types of correlations. You have a correlation and an anti-correlation. And this has been associated that when you see the correlation, the source is in the subcritical regime, and when you see an anti-correlation, the source is in the supercritical regime. Now, why is this the case? Has to do with the height of the accretion column that changes differently whether you are in the one state or in the other, and because the cyclotron line is representative of the magnetic field strength at the location where the line is formed. Okay, so if the height of the accretion column changes, the energy of the cyclotron line will change. Now, there are several models. I don't want to go into details here. This is not my work. I have shown you several models here. Some of them are only applicable to one of the states, because what I want to focus here is in another aspect of the energy spectrum, which is the continuum. I want to see if the X-ray continuum can give us information about the two accretion regimes. Now, the X-ray spectrum of a BeXB binary of an accreting pulsar is well described by absorbed power law with a high energy cutoff. You also observe a black body component that is attributed to this hot spot on the surface of the neutron star, and then you have the cyclotron lines and the iron lines. Okay, but here I want to talk about the X-ray continuum, this power law continuum. Okay, now the simplest, the easiest way to characterize the X-ray continuum is through what is called the hardness ratio. Okay, hardness ratio is simply the ratio of the intensity in two different energy bands. You select a low energy band, which is called the soft band, and a high energy band, which is called the hard band, and you just calculate the ratio between these two intensities. Okay, so what can we do with this hardness ratio? It seems so simple that you may think, I mean, not much we can get out of it. No, well, what we can do is to create this kind of diagrams, the hardness intensity diagrams and the color diagrams. I don't know if you are familiar with these kind of diagrams, but this has been used extensively by people doing black hole binaries and neutron star low mass X-ray binaries. When the X-ray luminosity changes on many orders of magnitude, the source displays a particular pattern in this diagram. And this is the utility of this kind of diagrams, of the hardness intensity and color diagrams. It is the fact that the source displays these characteristic patterns. For that, as I said, you need the source has to, the luminosity has to change by a lot, by orders of magnitude. Otherwise, you only see a part of it. But again, in the case of black hole binaries, this characteristic Q-shape diagram where you can identify the different states, and for neutron star low mass X-ray binaries, again, I don't know if you know that there are two different types that are called atoll sources and Z sources, and the name is obvious when you see these figures. Okay, now what does a hardness intensity diagram look like in a BeXB binary? Here you have an example. On the left-hand side, you have the outburst, the light curve, count rate as a function of time. And on the right-hand side, you see the hardness intensity diagram. So at the beginning of the outburst, the source lies at the bottom of this diagram and moves from left to right. It makes a turn, goes up, reaches the peak of the outburst, and then goes down. And eventually, at some point, close to the end of the outburst, it makes again a turn, but this time moves from right to left. Okay, so clearly the source is displaying two different branches, the horizontal branch and the diagonal branch. Okay. Now, can we generalize this result to other BeXB binaries with just this KS 1947 that has this particular behavior? So what I did is to analyze 9 outbursts. This is some work that I did about 10 years ago. I went to the RxD database and I downloaded the data for 9 different outbursts of 9 different sources, 9 different BeXB binaries. And these are the light curves, the outburst profiles. And these are the hardness intensity diagrams for each one of them. Now, note the following. Before I showed this source, KS 1947, okay? Here I'm showing exactly the same data as before, but notice that here I'm using a logarithmic scale for the y-axis, okay? Compared to the linear scale that I used here. And that is the reason why the horizontal branch is no longer horizontal, but the black circles represent the horizontal branch, okay? While the open circles corresponds to the diagonal branch. So what we see here is that 4 sources display 2 branches and 5 display only the horizontal branch. Interesting. So why is that? And now what would be the physical meaning of these 2 branches? So we can ask these 2 questions. What is the physical meaning and why we see 2 branches in some systems and only 1 in others? Let's see. Here you have 2 other sources, the same, the hardness intensity diagram for 2 different sources. So let's recapitulate. So the horizontal branch is seen at the beginning and at the end of the outburst. So it corresponds to a low intensity state. The diagonal branch is seen at high luminosity, and the transitions occur when the luminosity goes above certain value. In this plot, I call it L0. What it is important here is that this L naught is different from different sources. As you can see, for EXO 2030, it is at about 10% of the Eddington value, while in VO 332 is 3 times that. Okay, so one is tempted to associate the horizontal branch to the subcritical regime and the diagonal branch to the supercritical regime. But if this is the case, if this interpretation is correct, then this L naught would correspond with the critical luminosity. So here you have a nice and easy way to estimate the critical luminosity from the observations. Now, let's see if we can use the same argument, the same interpretation to answer the second question. Why do we see 2 branches in some systems and only 1 branch in other systems? And for this, I'm showing these 2 sources. Why these 2 sources? Because, as you can see, they have the same peak luminosity. Obviously, the count rate is very different because they are at very different distances. But when you take that into account, when you translate count rates into luminosity, you realize that the peak luminosity is the same. Okay, 7 times 10 to the 37 x per second. But KS 1947 shows 2 branches and AO535 only 1. Okay, as I said before, the critical luminosity strongly depends on the magnetic field. So I'm going to use this very simplified expression that I took from Becker et al. That relates the magnetic field through the cyclotron line energy with the critical luminosity. Now, in case of AO535, we detect a cyclotron line at 46 keV, while in the case of KS 1947 at 12 keV. This means that the critical luminosity in AO535 is significantly larger than in KS 1947. And if you now compare the peak luminosity with each of these critical luminosity, we see that in the case of AO535, the peak luminosity is below or of the order of the critical luminosity, and thus it is why you see only 1 branch, while in the case of KS 1947, the peak luminosity is clearly several times larger than the critical luminosity. And that is why you see the 2 branches. If we now put all the sources together in this table, and this straight line separates the sources that you see, in which we see 2 branches that would correspond to the sources above the line, and below the line would be the sources with only 1 branch. And just focus, let's focus on the last column of this table, which is the ratio of the peak luminosity over the critical luminosity. We see that all the sources that show 2 branches is because this ratio is significantly larger than 1. I mean, this is obvious because by definition, you see if you want to detect the supercritical regime, you need to be above the critical luminosity. Okay, so the summary of the second part, the continuum emission, and that was the objective, the continuum emission can be used as a diagnostic of different accretion regimes and to estimate the critical luminosity. And also be careful because the X-ray luminosity is by itself, only the X-ray luminosity is not a good indicator of the accretion regime, because we have seen that 2 different sources had the same X-ray luminosity and maybe in different states. Okay, so just to finish, this part is shorter than the other ones, so I did 10 more minutes. The third part is about what happens when the the two components interact. Okay, and as you can imagine, what happens is that they produce an X-ray outburst is produced. Now, although it is common understanding that the outbursts are caused by the mass transfer from the B disk to the neutron star, the details are uncertain. Okay, I said before that the disk in BeXB binaries is truncated, right? So if the disk is truncated, accretion of large amount of matter will only be possible if the disk has become sufficiently asymmetric and dense to overcome this truncation radius. The current idea is that giant outbursts occur when the neutron star captures a large amount of gas from warp, misaligned, and eccentric disk. Okay, and here I'm showing some simulation from Rebecca Martin. The initial state is this first rod with the black background, but you start with a symmetric but tilted disk. You run the simulation. In this case, the unit of time is the orbital period. So you see that after several orbital passages, the disk becomes distorted, eccentric, some spiral arms form. And at some point, in this particular case, after 22 passages, the neutron star is able to capture a large amount of matter from one of these parts of the distorted disk. Okay, you see a huge increase in the mass accretion rate, which means translate into an increase in the X-ray luminosity. Okay, now again, for the third time, what is the observational evidence that we have warp disk during giant outburst? Okay, one piece of evidence comes from the spectral lines. Okay, in B stars, the H alpha line appears in very different shapes, from single peak, double peak. You may also have symmetric, asymmetric profiles. And the different shapes are attributed to different inclination angles. When we see the system at low inclination angles, at face on, we see single peaks. And when we see the system at a high inclination angle, H on, we see this characteristic double peak profile where the central absorption goes beyond the continuum. This is known as a shell profile. And an intermediate inclination, we have double peak profiles. Okay, but what if we see all these different profiles in the same system, like in this case, in 4U115? That we see single profiles, shell profiles, double peak profiles. Since the rotational axis of the B star cannot change on time scales of a few weeks, that it is the characteristic time scale to see these changes, we must conclude that is the disk axis what it is changing. In other words, that we have a warp precessing disk. Now, if this is the case, then we can turn to a different technique in astronomy, not spectroscopy, but polarimetry. Remember that the light coming from a B star is polarized, and the linear polarized light results from Thomson scattering when photons from the star are scattered with electrons in the disk. But the critical point here is that the net polarization is perpendicular to the scattering plane, which in this case coincides with the disk. So if we have a warp precessing disk, we should expect to see variations in the polarization angle. Is that the case? Now, what I'm showing here is, well, the evolution of different optical parameters for the same system. For U of 115, we have how the equivalent width changed in the last 10 years. The continuum emission in the R band. The lower panel corresponds to the X-ray emission. And also I'm showing some of the polarimetric parameters, the polarization degree and the polarization angle. Now, in 2015, the source went through a giant outburst, a type 2 outburst, as you can see, the lower panel, but unfortunately, we didn't have enough observations to get to any, for a meaningful study of anything. But in 2017, the source went into a different, and again, to a type 2 outburst, and in this case, we were able to get more data. If we zoom in on the polarimetric parameters, what you have on the top panel is the polarization angle. In this figure, the dot lines corresponds to the beginning and end of the X-ray outburst. The dot dashed line corresponds to periastron passage, and the arrow means the peak of the outburst, the X-ray outburst. This is just for reference, but because here the interesting thing is the variation in the polarization angle, which about an orbital period before the start of the X-ray outburst, the value of the polarization angle was in agreement with the long-term trend, the historical trend of the source. Now, something happened, and the polarization angle changed, went up and down. So, how to interpret this? Well, why not as a proof that we have a precession disk, more precession disk? Well, I don't know. I mean, the theoreticians that model this will tell me if whether the amplitude that we see, the amplitude of change, which is just 10 degrees, and the time scales of this change, which is about 3 months, can be interpreted in that way. Okay. Of course, unfortunately, and as far as I know, this is the only case in which this has been seen, but not because it doesn't happen, it's because we don't have data. Okay, as far as I know, I mean, it's not easy to find, simultaneous polarization data with X-ray outburst. And in any case, it's not only that you have simultaneous with X-rays, you need to have polarization data before, I mean, several weeks or months before and several weeks or months later, because you never know what is the typical time scales of this precession disk. Okay, so the summary of this part is that polarization provides further evidence for the presence of highly distorted disk during the type 2 outburst, but more data are needed. On my last slide, that's the takeaway messages is that BeXB binaries are interesting objects because they are laboratories to study the physics of accretion, the interaction between the accretion and accretion disk. Disk in BeXB binary are truncated, denser and smaller than in classical B stars. The shape of the X-ray continuum can be used to study accretion regimes and estimate the critical luminosity, and optical polarization provides a direct way to test current models that explain type 2 outburst. Thank you very much for your attention, and I'm done.
All right, thank you very much, Dr. Reig. So I guess on behalf of everyone, I'll just give you some applause. We are going a little bit over time, so just to be mindful of everyone's time, I think we'll take a couple of questions quickly. And Dr. Reig, if people have more questions, would it be okay for them to get in touch with you by email afterwards?
Yeah, no problem.
Excellent. All right, so do we have a few questions for Dr. Reig? So maybe I had one quick one regarding the last point that you made for polarization. Oh, so I see Dr. Putschmidt has one. Maybe you should go ahead first.
No, just you please go ahead.
Okay, I was just going to say maybe if you can give a few quick words on what would be kind of your wish list for observational strategy in order to get more of these observations. If there's anything that would be kind of feasible in that sense.
No, I mean, in observational astronomy, all depends on the observations and the availability of observing time. That I mean, it's quite expensive if you want to use the big telescope. The interesting thing is that you don't need to have that big telescope in general. I mean, it depends. In BeXB binaries, the magnitude goes from 8 in the B band from 8 to 15, 16, 17. So you have a good range of sources, and most of them are visible from a smaller telescope. But of course, you need to have polarization instruments, polarimeters, and this is not as common as spectrograph or just a CCD. In our group, since 2013, we have a polarimeter, RoboPol, that in principle it was installed for a different purpose. It was installed to study blazars, but that I have been using it to monitor BeXB binary in optical polarimetry, and so I now gather a huge amount of, well, not huge because the observations are not as frequent as it would be as I would like. But still, you need, as the problem with BeXB binaries is in order to see changes, you need months or years. So normally observations are rather sparse. So for this particular case, you need to have ideally own your own instrument, or be able to have a collaboration with someone that has a lot of access to polarimeters, and be keep an eye on all these all-sky monitors on the X-ray emissions, where you can detect an X-ray outburst, hopefully at the beginning of the outburst, because that's the other problem. Being transient sources, you normally miss the beginning of the outburst. When you realize that it's in an outburst, you have already lost, the first week or so. But with these all-sky monitors, and you can get a quick response, and if you can also respond quickly to your optical observations, that would be ideal. But as I said, because the precessing time of the disk can be months, different months, I don't know, 6 months, 9 months, 3 months, 1 year, you need constant monitoring. You need to have constant monitoring in the optical.
Great, thank you. And maybe hopefully someone in the audience might have access to a polarimeter that could get in touch with you. So we have time, I think, for 3 more questions. So I have Katya, then I have a question from the chat, which I'll ask, and then Doug, and then other people can maybe reach you by email afterwards. So Katya, please go ahead.
Okay, so thank you for a very interesting talk. I'm especially interested in the hardness intensity diagrams. I haven't looked into that as much as I maybe should have or wanted. So maybe my question is already solved, but I was wondering about 2 of the sources. So AO535, where you said in the data set that you presented, it did not reach, or it just barely reached the critical luminosity. There have been very, very high flux outbursts, maybe observed with integral. So I wonder whether it went beyond the critical. I thought I did, but second part to the question, the other source is Swift J1626, which I do think has a cyclotron line measurement. And I think there was no cyclotron line listed in in your table.
Okay, yeah, okay. Maybe I should update this slide. It is true for AO5305. It has been. It went through a giant outburst recently, a couple of years ago, and it was the brightest ever outburst recorded for this source. And in that case, it was also observed by the Chinese mission HXMT. There's a huge amount of data from this mission, and indeed, it went through it passed the critical luminosity and went into the supercritical regime. And then you saw that the two branches in the diagram. Yes, you are right, and I should have included that in the talk. It is yes. The data that I showed was from XTE from years ago, but the outburst that this source showed a couple of years ago shows that it went into the supercritical regime. And yeah, I'm sure you are right about the cyclotron line. I haven't checked, but I should check that. Now, don't know if you remember. Do you know what is the energy of that cyclotron line for this system?
I should. I think it's rather low energy. I think 12.
Okay. If it is low, it's fine. It agrees with the
Yeah,
model with the discussion.
Yeah, I think so. So I think about around 12 keV.
Okay, in that case, I mean, it would be completely killing for the discussion if the cyclotron line is 40 or 50 something, because then you should, it would be contrary to what I said.
Yeah, no, very, very interesting. I have to be more aware of the hardness intensity diagrams. Thank you.
Okay.
The next question is from the chat. So Sunwoo Kim asks why MWC 656 may not be a black hole system.
Well, as far as I know, I can give, I don't know, I see, okay. Can give you the reference. All this comes from radial velocity measurements, right? Let me find the slide. Okay. This was done through radial spectroscopy, optical spectroscopy. Okay, so Jorge Casares back in 2014 did some observations and used, I think it was a helium-2 line that was supposed to come from the possible accretion disk. Anyway, they reached the conclusion that in their solutions that the minimum mass was about 4 solar masses. Now, these people, Janssen and collaboration, but also another group, Rivinius and Dietrich Bader, that I think is in the audience, has also done more observations, and from their analysis with new observations, new data, probably, I don't know, probably using different lines, they have reached the conclusion that the mass that Casares found was overestimated, and that by a factor of 2 or 3. And the new data rules out the black hole candidate. But I can only refer you to this reference.
Great, thank you, Dr. Reig. In the meantime, Katya mentions that the line energy is actually 10 keV. So now Doug has a question.
Hello, Pablo. Thank you very much. This very interesting work that you've summarized so nicely. I had one question that I was just curious about your opinion about the longevity of the magnetic fields of the neutron stars. Is there any evidence that they are spinning down or that they might be losing magnetic field over time? What I'm curious about is, could we expect that there might be a population of EE plus neutron stars that do not have big magnetic fields and might appear X-ray quiet?
Well, I don't know is the answer. I don't know. As far as I know, I've never encountered any reference to field decay in BeXB binaries. Field decay exists in isolated, of course, in isolated neutron stars. Probably we don't know enough about the magnetic fields in BeXB binaries. As far as I know, I don't know any field decay among these systems. So I'm afraid that I cannot answer. It is interesting what you say, but I cannot provide an answer to this.
And from the chat, I guess Dietrich Bade also says that it's an excellent idea from Doug. So this leaves us with one last question from Suman Bhattacharya in the chat, who says, thank you for the excellent talk. I have one very generic question about how such BE star on the main sequence and evolved neutron stars stays in the binary system, and asking for your comments on the evolution of such systems.
Okay, again, I'm not expert in the evolution of the systems, but I mean, the basic understanding is that when you have two initial massive objects and then one transfer mass from the other to the other, and one explodes. The initial higher mass star gives mass to the other one, and it is this second star that explodes as supernova first, leaving this neutron star. I don't know. I know that some people in the audience actually may be more competent to me to explain all this evolution of the X-ray binaries and the BeXB binaries. I know that there are suggestions that indicate that the B phenomenon is because of binarity, in the sense that all B stars, not talking about BeXB binaries, about B stars are binary systems. This has been suggested. Other people, well, are against this idea. But I don't know. I don't know what to say in terms of evolution. That is what I know.
All right. So I think we're now about 15 minutes over. So let us thank once again Dr. Reig for a really nice and stimulating talk. So thank you very much. And for everyone, I'll mention that there will be one more seminar of the working group on active B stars this year, which will occur next month. So I will be sending information about this shortly, so keep posted. So once again, thank you, Dr. Reig. This talk will be available on YouTube, so especially if some people had to drop off early and want to see the end of the questions, they'll be able to do so. And if you have other questions for Dr. Reig, please feel free to get in touch with me and I'll relay them over to Dr. Reig. So thank you once again, and have a good rest of your day.
Okay, thank you.
Bye, everyone.
Bye.